this computer. Okay, so we're ready. So let's start by practicing formulation of LPP, again, and solution of LPP using graphical methods, and then we'll get to next topics after that. Okay, so let's look at a simple example. So Reshma wishes to mix two types of food, P and Q, in such a way that vitamin contents of the mixture, we revised the problem that we solved. Okay, all right, fine. I think that's what I expected. All right, fine. We'll do that one first. Where is it? Here. Okay, so, all right, so basically, right. Okay, so we'll start with this problem again. So last time we had talked about this problem in detail. So we were looking at the product mix problem at Shader Electronics. They can produce two products. One is called the Shader X-Pod, which is a portable music player, and Shader Blueberry, which is an internet-connected color telephone. And we have to determine the mix of products that maximizes total profit. Okay? Now, what is given to us is this data. So we're given per X-Pod how many hours are required in the electronics and assembly department to produce, and per Blueberry how many hours in the electronics and assembly department, and the available time in the electronic and assembly department this particular week. And we also have the profit contributions of X-Pod as well as Blueberries. Okay, so the basic goal here is we need to determine how many X-Pods, so that's why the decision variables are the number of X-Pods to be produced and the number of Blueberries to produce. So in a product mix problem, always the decision variables are the quantity of each of the products to be produced. And the whole point is everything is expressed in terms of that. Everything that we have here is expressed in terms of that. Right? So let's first look at our objective. What is our objective? Our objective, of course, is to maximize total profit. Now, what are the profit contributions given? Well, each X-Pod gives us a profit of $7. Each Blueberry gives us a profit of $5. So if I produce X1 X-Pods and X2 Blueberries, my total profit will be 7X1 plus 5X2. And that's what I want to maximize. My objective function is to maximize the total profit. X-Pods give me $7 each, so 7X1. Blueberries give me $5 each, so 5X2 from there. And we're trying to maximize the total, 7X1 plus 5X2. Now, what are the constraints? Where do the constraints come from? Well, the constraints come basically from the hours available, the time available in the two departments. So let's look at it in terms of each department. So let's look at it first in terms of electronic department. In the electronic department, so X-Pods require 4 hours per X-Pod, and per Blueberry we require 3 hours. So for X1 X-Pods, how many hours of electronic time do we require? 4 into X1. For X2 Blueberries, we require 3 into X2. And so the total time requirement in electronic department will be 4X1 plus 3X2. And that has to be less than or equal to the time available, which is 240. So electronic time required is 4 into X1 plus 3 into X2, the left-hand side. And the right-hand side is the availability, that is 240. Similarly with the assembly department, each X-Pod required 2 hours of assembly time, and each Blueberry requires 1 hour. What happened? 1 hour of assembly time. Okay, so each X-Pod requires 2 hours of assembly time. Each Blueberry requires 1 hour of assembly time. So assembly time requirement is 2 times X1 for the X-Pods, 1 times X2 for the Blueberries. So total assembly time required is 2X1 plus X2. And that has to be less than or equal to 100. Okay, so those are the two constraints. Of course, one more constraint is that, of course, we cannot produce negative quantities. So x1 and x2 must be non-negative. Now, to solve this, we discussed the method known as the graphical solution method. Okay, so where we have a two-variable linear programming problem. So when we have a two-variable linear programming problem, we can use this method. Of course, when there are too many constraints, it's very messy, but still it can be used. If you're very careful, it can be used. So first thing is to plot the constraint equations at their limits by converting each equation to an equality. So construct both of those. Then find the feasible solution space. The feasible solution space is the set of all points satisfying all the constraints. In this case, it's the set of all combinations of XPODs and the set of all combinations of XPODs and blueberries that we can make with the given resources. With these given resources, what are all possible combinations of XPODs and blueberries that we can make? That's called the feasible region. Oh, I went too far, sorry. Okay, so first thing to do is, all right, so we're taking x1 as the number of XPODs on the x-axis and number of blueberries, x2 on the y-axis. And first we look at the electronics time. What was the electronics constraint? That constraint was 4x1 plus 3x2 less than or equal to 240. So first we'll think of it as equal to 240. So what does that mean? That means we're using up all the time available in the electronics department. Now, when we want to see where it hits the two axes, we put one variable equal to 0 each time. So when we put x2 equals 0, we'll get 4x1 equals 240. So x1 equals 60. And when we put x1 equals 0, we'll get x2 equals 80. These two will plot on the axis. Okay, so on the x1 axis, we see that we've taken 60. On the x2 axis, we take 80. And we join these by a straight line. Now, what does this straight line mean? All possible. So it's the set of all possible combinations of XPODs and blueberries that we can make with the given time available in electronics department. Similarly, we have to do the same thing with assembly department. So 2x1 plus x2 was less than or equal to how much? 100. Make that equal to, so we'll get 2x1 equals 100, x1 equals 50, and the other one, x2 equals 100. So the intercept points are 50 and 100. 1 second. And let's say, hello? Natasha? Hello, sir? Sir, you left your pen drive here, sir. Hello? Hello? I'm able to hear at all. Okay, anyway, I'll call him back. Okay, so in a similar way, for assembly time, if we make XPODs only, it's 50. If we make blueberries only, it's 100. So we join these two. So all possible combinations that we can make using all the assembly time. And we want points that lie below both of these lines. For it to be feasible, we look at all combinations that satisfy both of these constraints, less than or equal to both of these constraints, and in above the x1 axis to the right of the x2 axis. This gives us our feasible region. Hello, sir. Sir, you left your pen drive here, sir. Okay. Yes, sir. Yes, sir. Yes, sir. Sure, sir. Of course, sir. Yes. Right. Yeah, that's it, because I thought pen drive is very important, no? So, okay, sir. Sure, sir. Right. Okay, yeah. Okay, so the overlap region of both of the constraints is what is called the feasible region. The set of all points satisfying all constraints. In other words, this is of all combinations of exports and blueberries that I can produce with the given resources. Now, out of these, I want the optimum value. I want the solution that, or the combination that gives me maximum total profit. Again, there are two ways of doing this. One is using the isoprofit line method. In the isoprofit line method, we'll start with some profit level, see whether we can improve this, and find the point that is tangent, or the line, isoprofit line, that is tangent to the feasible region. So we'll start with profit level of 210. The intercept points are 30 and 42 for that. And so this is that line here. So 42 on this side, 30 on this side, and they've joined it. So this black line is the isoprofit line that yields a profit of $210. Now, how do we tell whether this is optimal or not? Well, if there are points in the feasible region above this line, it's not optimal. So clearly this is not optimal. So we're going to look at some values slightly higher than this. Now we look at 280. Again, we find that there are points in the feasible region above this. So we take another value, 350. Again, we can see that this is not optimal, and so on. Next one is 420. Actually, that goes outside the figure. The optimum is at 410, which is tangent at this corner point here, the corner point there. Okay, so finally, the optimal point is where the maximum isoprofit line becomes tangent to the feasible region, and that happens at x1 equals 30, x2 equals 40, and the profit that we make in this point, at this point, is 410. Oh, 8. All right, yeah, so x1 is done, x2 equals 0. Yes, exactly. Is it assumed? Yes, yes, of course, yeah. Is it as per the question? Yes, it is as per the question. Yeah. So, why we took 50? Because of this, okay, right. Oh, sorry, I didn't observe at the time. Okay, so what happened next? Okay, optimum point is this, and so. Okay, good. So, now, of course, this isoprofit line method is good, but the point here is it's a bit cumbersome drawing these parallel lines, and sometimes it's not clear where the corner point, because if they're very close by corner points, it's a bit difficult. So, a much better method is from the following observation. So, because we're taking straight lines, and because the feasible region is bordered by straight lines, clearly, one of the corner points has to be optimal. It cannot be an interior point, it cannot be a boundary point, any point on the boundary. It has to be one of the corner points. So, rather than doing this method, a simpler method is identify the corner points, identify each of the corner points, evaluate the objective function at each point, and see which one gives maximum. In this case, we want maximum. In the case of minimum, find the one that gives minimum. Very, very simple method. So, first one, of course, optimal value will always be at a corner point. Find the objective function value at each of the corner points and choose the one with highest profit. Well, one obvious corner point is 0, 0. And of course, if we don't produce anything, we can't expect any profit. In the next one, 0, 80, that was the one on the x2 axis. The profit is 7 times 0 plus 5 times 80, which is 400. In the other one, 50, 0. Okay. Profit is 7 times 50 plus 0 times 5 times 0, which is 350. And the last one is the intersection. How do we get intersection of constraints? Well, we solve them simultaneously. So in this case, we multiplied 2 times the second constraint. So 4x1 plus 3x2 equals 240. Multiplied 2 times this, so 4x1 plus 2x2 equals 200. When we subtract, we end up getting x2 equals 40. And when you substitute this back, you'll get x1 equals 30. Okay, x1 equals 30. So the corner point is 30, 40. And then When we substitute that into the objective function, we'll get 7 times 30 plus 5 times 40 is 410. Sure. This one? Yeah, because what we're doing is, see, we want to cancel out one of the variables. So this was, first equation is 4x1 plus 3x2 equals 240. To make this similar, to be able to cancel this out, I can multiply this one by 2. So I get 4x1 plus 2x2 equals 100. And then I just subtract first equation minus second equation. So this minus this is 0, this minus this is this minus this is that. So I'm just subtracting. Right? I'm getting rid of, this is the process called elimination. This is one of the common solution methods called elimination. Of course, nowadays if you have calculators or even in Excel also, very, very simple to calculate intersection points without any hassle at all. Okay, so we end up getting this. All right, we'll come back to sensitivity analysis. That's a very important aspect. Okay, we can solve this one also. Huh? All right, why not also do this one? Okay, so that was a maximization problem. Let's try to solve minimization problems. Oh my God, what is this? Just going ahead of itself, huh? Solving minimization problems. Okay, so, okay, no, we'll come back to this, don't worry. Okay, so let's see this. So, basically, it's very much the same way. I don't know why they have to have a separate heading for this. Formulated and solved in the same way as maximization problems. So this time, ISO cost line. And when we're minimizing, we move towards the origin. When we're maximizing, we moved away from the origin. When we're minimizing, we move inwards towards the origin. Okay, so here's an example. So suppose we have, oh, they've given everything, yeah? All right, I suppose the case must have been in the textbook, but basically, number of tons of black and white picture chemical produced, so there's some chemical industry, and color picture chemical produced. And the total cost is 2500 x1 plus 3000 x2, 2500 x1 plus 3000 x2. And what are the constraints? Well, at least 30 tons of black and white chemical must be produced, at least 20 tons of color chemical must be produced, at least 60 tons total must be produced, and of course, x1 and x2 are non-negative. Why this is dollar sign? I'm not sure, but okay. Obviously not needed. Dollar sign is not needed. Okay, so how do we construct the feasible region? Well, first constraint is x1 greater than or equal to 30. Okay, so what will that constraint look like? Well, it will be a vertical line at 30, right? So when you have just a single variable, x1 equals 30 is a vertical line at 30. So when we do this, so a vertical line at 30 is our first constraint. x1 greater than or equal to 30 means it should be to the right of this vertical line. Everyone agrees? Okay, so that's our first constraint. Second constraint is x2 greater than or equal to 20. Now that's a horizontal line. So when I have a form of x1 equals constant, that's a vertical line. If I have the equation of the form x2 equals constant, that's a horizontal line. So we'll have a horizontal line at 20, and it has to be above that horizontal line. So vertical line at 30, to the right of that line we want, and horizontal line at 20, we want above this. Then our next constraint was x1 plus x2 greater than or equal to 60. So on the x1 axis, we'll have 60 here. Okay, so this point on the x1 axis, so it'll cut the x1 axis at 60, x2 axis at 60, and we just join these two together like this. And again, it has to be above this line. Yes? Any other constraints were there? No, no other constraints. Now, in this feasible region, therefore, so we have these things. Where is our feasible region? It has to be above this line, to the right of this, and above this line. So it's this shaded, well, this above space there. This shaded region is our feasible region. And amongst these, we want the point with minimum total cost. So if we use the isocost approach, we can draw a line and then bring it down. But you can clearly see it has to be at one of the corner points, A or B. Clearly, the minimum cost point will not be further and further out. It will be as close to the origin as possible. So it has to be either A or B. And how do I get A or B? Well, I get B by putting x1 equals 30 in the equation. So that's 30, 30. I get A by putting x2 equals 20, 40, 20. So it's either 40, 20 or 30, 30. Find the total cost at each of these. That's basically how we do this. Anyhow, let's see what they say. Total cost is at 40, 20 and 30, 30. So clearly, which one has least total cost? A, at A, right? So 1,60,000, the total cost there. And so, in this case, our optimal solution is x1 equals 40, x2 equals 20. Okay, so, all right, this is interesting. Okay, so, do you want to try one more product? Okay, no, we'll do some simpler ones. We'll come back to this. Let's do some simpler examples. Okay, so, all right, so this is second one, first one. So, Reshma wishes to mix two types of food, P and Q, in such a way that the vitamin contents of the mixture contain at least 8 units of vitamin A and 11 units of vitamin B. Okay. Food P costs 60 rupees per kg and food Q costs 80 rupees per kg. Food P contains 3 units per kg of vitamin A and 5 units per kg of vitamin B, while food Q contains 4 units per kg of vitamin A, 2 units per kg of vitamin B. Determine the minimum cost of the mixture. So, what do we need to decide? That's the objective, but what are the decision variables? What levels do we need to decide? What are we trying to decide here? A combination of, so how much of food P and how much of food Q to consume so as to meet the vitamin requirements at minimum total cost. So how much of each of the foods should I consume so that I can meet my vitamin requirements at minimum total cost? Yes? So our decision variables are x1 is the quantity of food P to be consumed, x2 is the quantity of food Q to be consumed. What is the objective function here? The total cost. So food P is 60, so 60 into x1. Food Q costs 80, so 80 into x2. So we're minimizing total cost, which is 60 x1 plus 80 x2. Let me just try to, we don't have that stylus, huh? Okay. One second, let me see if we can. There's no other way of writing it, huh? Okay. All right, we'll otherwise try it with a pointer. See if it can be done well with it. If it doesn't work, then we'll try to get that. So we're trying to minimize. Oh, God. All right, anyhow. Sorry for the bad handwriting. Total cost, which is 60 into x1 plus 80 into x2, right? All right, that's okay. All right, fine. Somehow it's okay. All right, now, what are the constraints here? What are the constraints? Okay. Okay, so we want at least 8 units of vitamin A. And how do we formulate that constraint? Vitamin A should be 8, vitamin B should be 11. All right, so how do we express that in terms of x1 and x2? Well, if we look at food P contains 3 units per kg of vitamin A, and food Q contains 4 units per kg of vitamin A. All right? So one unit of food P contains 3 units of vitamin A. So X1 units contains 3X1 units of vitamin. So 3X1 is the quantity of vitamin A from food P. And 4X2 is the quantity of vitamin A that I get from, no, 4. Food Q contains 4 units vitamin A. Now don't look at the other one. So 4X2, and this should be at least 8. We want to have at least 8 units of vitamin A from this mixture. Now, if we look at food, at vitamin B, we have 5X1 is the amount of vitamin B that I get from food B, and 2X2 is the amount I'm getting from food Q. That has to be greater than or equal to 11. Of course, X1 and X2 should be non-negative. All right, just 1 second. Let me just check one interesting thing, if possible. Oh. Yes. Okay. Now, I'm going to, well, of course, we can practice, all of you will have to practice the graphical method, but I'll do this using a software called Tora. Okay? This nice software allows us to solve these things in a very simple way. This is along with a book by Taha's Operation Research and Introduction. That's why T-O-R-A. T-O-R-A is the name of the software. But anyhow, let's just use it. I'm going to solve linear programming problems with this. Okay, so the nice thing is the graphical output. We can solve also in Excel. I'll show you that also a little later. So 2 and 2, right? So 2 variables, 2 constraints, right? So what do I have here? Food P cost was, oh, by the way, first thing is that this is maximizing. What we're doing here is we're trying to minimize, right? So minimize, if you just click that, it becomes minimized. We're minimizing 60X1 plus 80X2, correct? And what did we have here? 3X1 plus 4X2 is greater than or equal to how much? 8, right? And 5X1 plus 2X2 is greater than or equal to how much? 11. Okay, so we've entered all the data and we're going to solve the problem graphically. Okay, we'll talk about other methods a little later, but so we have this. So let's go through this carefully. So when you put x2 equals 0, we'll get 8 by 3. 8 by 3 is how much? Around 2 point something? 2.67. So somewhere here it will come, right? And on the other side, we'll get 2. So 2 and 2.7, 2.67 will come. So if we just click that equation, it will draw that graph for us. On the x1 axis, 2.67. On the x2 axis, 2. And it has to be above this line. So the other one, 11 by 5 is 2.2. So that will be somewhere here. And 11 by 2 is 5.5. So that will be somewhere over there. Okay, so again, we click this. And because there are only these 2 constraints, this whole thing is our feasible region. All points above both of these lines. So the corner points are these 3 corner points here. Okay, one of these has to be minimum. And so now if we click the objective function, for example, it will find the minimum point. So the minimum point is x1 equals 2, x2 equals 0.5, and the value of the objective function is 160. So that says we should have 2 kgs of food P, half a kg of food Q, and the total cost is minimum is 160 rupees or whatever. Okay. By the way, because it's at the intersection of these 2 points, because it's at the intersection here, okay, because it's at the intersection here, what this also tells us is that we are meeting both requirements exactly. Okay, so we're meeting both vitamin A and vitamin B requirements exactly by doing it. Right? Exactly, we're meeting the requirements. Okay, so everyone has understood? It's a very useful software for visualizing these types of things. So, all right, so shall we do some more of these? Right, so let's try the next thing. So, one kind of cake requires 200 grams of flour, 25 grams of fat. And another kind of cake requires 100 grams of flour, 50 grams of fat. Find the maximum number of cakes that can be made from 5 kg of flour and 1 kg of fat, assuming there's no shortage of other ingredients. Other things, sugar, other things are unlimited. So, what are we trying to do here? What do we need to decide? Quantity, okay, of cakes of each type do we need? How many cakes now? How many cakes of each type we need to make with given resources to maximize the total number of cakes? So, if X1 is cakes of first type, X2 is cakes of second type, what is our objective? What is our objective function here? Number of cakes means X1 plus X2. Very simple in this case. So here we're maximizing. So maximize Z, okay, Z is just a name, X1 plus X2. That X plus looks like a multiplication sign, but anyway, I'm sure you understand, no? Okay, so what are the constraints? Right? First, in terms of flour, right? So each cake of type 1 requires 200 grams of flour. So 200 x1 is the amount of flour required for cakes of type 1. Each type 2 cake requires 100 grams of flour. So 100 x2 amount of flour is required there. And this has to be therefore less than or equal to how much? 5 kgs. What is 5 kgs? 5,000, right? Remember, those are in grams. This is in kgs. So, all right, what is the matter? Solve the minimize and clarify the minimized part. Can you please solve the minimize and clarify the minimized part? I didn't understand. Hello? I think this is Vivek, right? No, audio is clear, yes. The previous problem, huh? Oh, which one? The vitamins one, okay. What was the, okay, we'll just finish this one, 2 minutes, and then we'll go back to vitamins. Solve the minimization one, okay. All right, anyway, so we'll go back in a moment, okay. So here, now that was the flour constraint. Let's look at fat constraint. Oh, what's wrong? Here, no, 25, sorry. 25x1 is the amount of fat required for type 1 cakes. 50x2 is the amount of fat required for x2 cakes, sorry, type 2 cakes. And what is the total fat available? 1 kg, which is 1,000 grams. And of course, x1 and x2 should be non-negative. Non-negative, right? We can't make negative cakes. Otherwise, see, the problem is, if we allow x1, x2 to be negative, then we'll take out resources by taking negative cakes and put them in the other. That shouldn't be. It's like sort of eating or uneating a cake or something like that. It's a very strange type of concept, right? So you'll create some new resource by taking negative cakes or whatever. Okay, so let's see how we can do this. Okay, so let's keep all of these. All right, so now wait, just while we're at this, so what were you saying, Vivek? You wanted some clarification on something here, right? Can you please solve the minimize? Solve the minimize, huh? Okay, all right. So you want me to actually find the corner points and so on? Hello? Then? I didn't understand what exactly you wanted. The minimum cost. Oh yeah, we got that, right? The minimum cost was, oh, acha, okay. All right, we'll have to do it again. We click that first. Oh, you didn't understand it. Okay, all right, fine, we'll do it, no problem. Okay, so we had done it this way. Now, the whole point is, okay, in fact, we can just go back and solve it again until we actually solved, okay? So, all right, first, at least did you understand the constraints? You understood this drawing the graph, right? You understood this graph part? Okay, so from this graph, let's see how to get the solution, all right? So now, out of these, there are 3 corner points that can be minimum, right? We have this point here, and this point here, correct? Now, this point here is, I think, 2.67, 0, right? This point is 2.67, 0. This point is 0, 5.5, right? So, we have 2.67, 0 and 0, 5.5, and the intersection of the 2 lines. All right, to get the intersection of the 2 lines, let's just multiply the second equation by 2. So, we'll get 10x1 plus 4x2 equals 22. Subtract them, so you'll get 7x1 equals, what is 22 minus 8? 22 minus 8? 14, right? 14 divided by 7 is 2. So x1 equals 2, and then when you substitute, you'll get x2 equals 0.5. So there, okay, let me go back to the PPT here, okay? So the corner points that I get here are as follows. The corner points that I get are as follows. Oh, where's the pointer? The corner points are 2.67, 0, 2, 0.5, and 0, 5.5. Right? Okay, now we need to find the total cost at each of these points. So the total cost in the first case, total cost in the second case, total cost in the third case. So what is the total cost here? 60 into 2.67 or whatever is 120 plus 2/3 is 40. 120 plus 40 is 160. Okay. In this case, 2 into 60 plus 0.5 into 80. So 120 plus 40 is again 160. And in the last case, 0 into 60 plus 5.5 into 80 is how much? 440. So out of these, which one is minimum? Actually, it turns out both of these are minimum. Right? In this case, this is called the multiple solution. Right? Both of these points are minimum. Okay, so both 2, 0.5 as well as 2.67, etc., 0 are both minimum. In fact, actually, if you look at the solution there, oh, not this one. If we look at the solution here, where is it here? Okay, so when we do this solution, all right, you'll see that the isoprop cost line coincides with this. So actually, both of them are identical. So all points on this line will be optimal. So all points between that 2, 0.5 and 2.67, 0, all points will be optimal actually. So This is a very special case. Okay, so it's not just this point, but all points on that line will be optimal. So maybe, anyway. All right, so did you understand now? Okay, good. All right, now let's get on to our next problem. Okay, can we solve that in Torah also? Shall we solve that in Torah also? Number of cakes? Not difficult. So we'll just, okay, we can just go back here and just modify everything. So I'm maximizing x1 plus x2, so the coefficients are 1 and 1. This is, was it 100 and 200 or 200, 100? 200, 100. 200, oh, 200 and 100. And this is now less than equal to, so less than equal to 5 kg, so 5,000. And this is how much? 25 and 50, right? And again, less than equal to how much? 1,000. Okay. All right. So we want to solve this now. So solve. Okay. So what do we do? So first, let's look at the flour constraint. So if I use all the flour to make type 1 cakes, I'll get 25. If I use all the flour to make type 2 cakes, I'll get 50. And so this is the set of all combinations of cakes that I can make with the existing flour, existing amount of flour. This is the set of all combinations I can make with the existing fat. So this is the feasible region. Okay. Now, out of these, which one do you think will be optimal? Well, it looks like the corner intersection point will be optimal. So, looks like it, but never know until we actually do it. Yes, the optimum point is x1 equals 20, x2 equals 10. So, we should make 10 cakes of type 1 and 10 cakes, 20 cakes of type 1, 10 cakes of type 2, and we'll get 30 cakes. And again, it being the intersection means we're completely using up all the flour and all the fat. Completely used up all the flour. Right? So, is this difficult? No? No problem, no? Oh, there's one. Why you used 1 and 1? Ah, yes. We used 1 and 1 here. 1 second. We used 1 and 1 here because they asked us for the total number of, so we want the maximum number of cakes. Maximum number of cakes means x1 plus x2. So what are the coefficients of x1, x2? 1, 1. Okay, that's why we used 1 in both cases. Okay? That's where the 1s came from. Alright, so shall we try one more or is it clear, no? Okay, let's look for some other more interesting one. Nothing is really interesting. Okay. In the last problem, yeah, in the last problem that was cost, right? The costs were given to us, right? The cost here was, see, these are objective function coefficients. The total cost was 60x1 plus 80x2. That's why the coefficients there were 60 and 80. But here, the objective function is to maximize total number of cakes, x1 plus x2. And the coefficients are therefore 1 and 1. Okay? All right, so let's look at our next thing in our sequence. Okay, we can do this. Okay, why not do this one? All right, one more shall we do before we get on to, oh, I don't think, anyway, we'll see. Okay, a factory makes tennis rackets and cricket bats. I don't know why they're making these two different, quite different things, but let's just imagine that they can. So tennis rackets and cricket bats. A tennis racket requires 1.5 hours of machine time and 3 hours of craftsman time while in its making, while a cricket bat requires 3 hours of machine time, 1 hour of craftsman time. In a day, the factory has the availability of not more than 42 hours of machine time and 24 hours of cricket time, craftsman time. Now, second part of the problem is important. So, if the profit on a racket and on a bat are 20 and 10 respectively, find the maximum profit of the factory when it works at full capacity. They're all similar actually. Right? So what are we trying to maximize? Profit. So we're trying to determine how many how many tennis rackets and how many cricket bats to produce. All product mix problems are of this form. Okay, how many tennis racket and cricket bats to produce to maximize our total profits. So we're maximizing. What are we maximizing? 20x1 plus 10x2. And, so we're maximizing. Oh God, even worse than before. All right, let's just call it Z. Objective function is Z. 20x1 plus 10x2. Okay. Now, what else is given? Subject to what? Well, first let's take machine time. So 1.5x1 is the machine time required for x1 tennis rackets. And how much is for cricket bats? 3x2. 3. No, read the problem carefully. Okay, so let me underline it so you can see. Okay, so look at machine time. Machine time, cricket tennis racket is, oh God, this is an underline. Huh? How do you undo? You have to erase it, is it? Okay. All right, so tennis racket requires 1.5 hours of machine time, and a cricket bat requires 3 hours of machine time. Okay, so I'm only looking at machine time. So tennis racket 1.5 hours, cricket bat 3 hours. So how many tennis rackets do I want to produce? X1. So I'll get 1.5 X1 from there, and 3 hours of machine time for cricket bat. So 3x2 from there. So 1.5 X1 plus 3x2 is less than or equal to how much time available? Yeah, if you can call. No, I don't think, it's coming now. Hello? We can hear now, see? It's coming.
But it runs out. The light on this one needs to keep going. The light here.
Okay, we'll just call him. We'll just get, what do you call it? We'll get a replacement one. Just 1 second, okay? Okay. Yes. All right. So can everyone hear? Account ma'am was using the scribble pad. Yeah. I think, right. Okay. Good. Right. Yeah. Okay. Good. So we'll work on that. Okay. So what was I saying? Yeah, we were about to solve that problem, right? Okay. Oh, what is this? Oh, this is another one. Oh, great. Oh, we've already solved that one here. Okay. So, yeah, just to finish off what we were discussing here, I tried to point out and show you. So, in the case of craftsman time, we see that for tennis rackets, each tennis racket requires 3 hours of craftsman time. So we'll get 3x1 hours of craftsman time there. And each cricket bat requires 1 hour of craftsman time. So 1 into x2 is from there. So total craftsman time required is 3x1 plus 1x2. And that has to be less than equal to the 24 hours available. Less than equal to 24. And, okay, let's solve this again in the way that we have been doing using Toda. Okay, so, and it's already a maximization problem, so let's just change. What are the objective functions coefficients now? 20 and 10, so we'll go here. So, coefficients here are 20 and 10. So, depending on what are the objective function coefficients, 20 and 10. So, what is the next one? What are the constraints? Here 1.5, 3 and 42. So 1.5, 3 and 40. Oh, what happened? 1.5, 3 and 42 is the total available. And here what it was? How much? 3, 1 and 24. Okay? 3, 1 and 24. Okay? Very, very simple type of problem. And so again, we'll solve this graphically. Oh, some comment. What is the answer? 3. Okay. You have put 25, huh? Is it? Oh, I see. Oh, that's... No, not that I put it. It was there already. We couldn't get rid of it. Yes. But good. All right. So let's solve it. So first one, of course, is the machine time constraint. So 28 on that side and 14 on that side. Okay. Next is craftsman time constraint. So I think 8 on this side and 24 on that side. And now, if we want to solve it, we find that again, by chance, the corner point and the intersection point is the solution. So how many of each? Well, 4 tennis rackets and 12 cricket bats is the optimal solution. And our profit contribution is 200. Okay? Very, very simple. Okay, so that's our optimal profit contribution. Okay, so now, as you'll see, most of them are very similar types. So try to go through the rest of these. Okay, here's another one. It's already formulated, luckily. So, can we do it in Excel? Yes. Okay, all right. Maybe, okay. All right, so who is this asking? Rajesh. Rajesh wants to do it in Excel. Okay, let me just do something else before doing it in Excel. All right, our data is here. Okay, so when we solve this, okay, we had shown you the graphical method. Of course, we're going to need a little more than just the graphical solution. So let me show you another place to find the solution. Okay, it's nice to see the graphs, but if you're only interested in the solution, one can also do the following. So go straight to the final solution. Right? And in the final solution, what we have studied so far is just this part here. So the values of x1 and x2 and the optimal objective function. So x1 equals 4, x2 equals 12, and z equals 200. Now there are some other things that we're going to study. Those are aspects of what is called sensitivity analysis. We'll be discussing that in just a few minutes after this, okay? So we'll be talking about the sensitivity analysis. Now, so this is one way of solving. Now let us also solve this in Excel as Rajesh was suggesting. Okay, so in Excel, it's actually not as, and actually, okay, I showed Torah just basically because of the graph. Actually, I think it's easier to solve things in Excel and easier to modify things. It's much easier to modify things and do whatever what-if analysis in Excel rather than in Torah. So my opinion is Excel is a better tool. Okay, so since we're solving solving that tennis and that problem, right? So this is our problem. Where did it go? Here. Okay. So we're maximizing the total profit contribution. So we'll start somewhere here, and we'll look at tennis rackets and cricket bats. Okay. Doesn't matter. We can just call it X1 and X2 also if you like. These are just the names of the variables, and these two spaces are where I'm keeping the variables themselves. Okay. Torah is a free software, but the problem is you need to know where to get it from. So you need to know where to get it from. I think I have a version. I think I can give you a version, but how can you get it from? But sharing online is difficult. I can give it to one of the people here, but then how to get it to you, I'm not very sure. If you have that Google Drive, you were saying. Someone had a Google Drive, huh? Okay. Just see if it can be shared through that Google Drive. I'll show you, okay? All right? Google Drive, yes. If it is free, we will get it, huh? I see. But be careful. There are other softwares also called Torah, and that is some SQL or something like that, some structured. Yeah, that's not the same Torah. So then you'll end up doing some search or something. So be careful, okay? Don't just take any Torah. All right. So tennis rackets and cricket bats, and I'm going to just sort of make this a little more. So generally, I sort of make it a little more clear that these are the variables. So those are the variables. So I've highlighted my variables here. Okay. Then I'm going to create my objective function in this row here. Objective function. Now, objective is total profit, of course. Total profit contribution. Huh? Now, what are the profit contributions of each of these rackets and bats and whatever? Well, this one is 20 and this one is 10. So I'm just writing down the coefficients here. And let's look at machine time and craftsman time. Let's just write down the basic coefficients that we had. So what were the coefficients? 1.5331. 1.5 and 3 and 3 and 1. Okay. Now I'm going to create the functions, the objective function Torah for linear program. Yes. Yeah. Okay. So I'm going to create my objective functions as follows. So what do I want? I want 20 into x1 plus 10 into x2. So a simple way of doing that is just multiplying this multiplied by this particular cell plus this multiplied by that particular cell. And I want those cells to be fixed because I'm going to copy them down. So what I'll do is I'll put a dollar sign. Everyone knows what a dollar sign does? Everyone knows why I'm putting a dollar sign? Because when I copy it, that same cell should be fixed. So when I copy it down, it'll be fixed. Now, why do I want to copy it down? Because all of them are similar form. Nah? So when I copy it here, these become 1.5 into x1 plus 3 into x2. And this one is 3x1 plus 1 into x2. Yes. Okay. Absolute value. What? Oh, absolute value. Yes. Fixing the absolute reference, it's called, not value. Okay. Absolute reference. Okay. So now the constraints I'm going to write down here, less than or equal to how much? How much was it? 42, I think. 42 and 24. Yeah, 42 and 24. Yeah, so, all right, and we're almost done. So this one, I'm just making it look nice. All right, so this is my objective function. These are the variables. These are the constraint left-hand sides. These are the constraint right-hand sides. Okay, so now I'm going to use an add-in called solver. Can I move this down? Yeah. Okay, I'm going to use an add-in called solver. Now, solver appears in the data tab on the right-hand side here. Okay, in the data tab, when we go to the data tab, right-hand side, it will appear. By chance, if it's not there, okay, so by chance, yeah, no, for those who don't know, if it's not there, you can bring it as follows, okay? So if none of these are, all right, so by chance, if you go to your data admin and see data tab and don't find anything on the right-hand side here, then we can bring it in as follows. So we go to Excel options, okay? Where's options? There's options, Excel options. Then on the left-hand side, you'll see add-ins, okay? Add-ins, and at the bottom, this manage Excel add-ins will appear. So go to Excel add-ins, and then just click this one. We will need this, of course. I think you need Excel, this analysis tool pack for descriptive analytics. Huh? So you need those also. But for us, we need solver. Okay. All right. And then in data analysis, you'll get. Okay. And we need solver. Okay. So now first thing is we go to the objective function cell. Wherever we are, we go straight to the objective function cell and open solver. Okay, so open solver like this, and you'll get this particular thing. Now, this basically, it says set objective. So is this our objective? Yes. And it's asking whether maximizing, minimizing, or setting the value equal to. Actually, this allows us to do either maximum, minimum, or it allows us to also make it equal to some value. Okay. So it allows us to solve equations also. That's why it's called solver actually. It solves. Yeah, sure. Can I finish it and then, yeah, I'll just finish it and then we can. Okay, so this is our objective, and solver allows us to either maximize, minimize, or solve an equation. We're not solving the equation, we're maximizing in this case. Now, where are the variables? Well, these two cells are the variable cells. Okay, these two are the variable cells and the constraints. Now, luckily in this case, both constraints are of the same type. So I can take the left-hand sides together and make them less than or equal to the right-hand side here. Okay, if they're different constraints, they have to be inputted differently, because if one is greater than or equal to, the other is less than, the other is equal to, those have to be inputted separately, because, well, obviously. Now, almost done. Almost everything is entered. We just have to go here and say simplex LP. Okay. Actually, simplex is a method okay. Anyway, I think we'll omit it for you. Okay. All right. Anyway, it's coming in one of the slides. We'll see. If you're comfortable with it, we'll continue. If you're not, we'll stop. Okay. All right. So simplex LP. Simplex is a method actually for solving this. We'll be looking at simplex method shortly. Okay. And now we just solve, and okay, well, the solution we've got really. So actually, we're going to need something called sensitivity analysis later. So it's usually a good idea to take the sensitivity analysis also. Well, here anyway, you can see the solution is 4 tennis rackets and 12 cricket bats, and the profit is 200 rupees. We can read it here also. The number of tennis rackets is 4, and the number of cricket bats is 12. You can calculate the thing by multiplying 4 into 20 plus 12 into 10, and then get the solution. That's another way of doing it. Okay. Okay. So, yeah, sure. We'll share the Excel. You can all see it, no? Yeah, I'm sure you can see it, so there shouldn't be a problem. All right? Yeah, so. Okay. Huh? Yeah, I'll put that. Reason is it was disturbing this. Okay. So you wanted to look once again about at the things, okay? So what did I do? Oh, I see. I'll have to pull this down. Okay, so basically I'm multiplying this into this plus this into this, and I'm fixing these two cells here. I'm fixing these two cells. Did the cells get out? No. See, no, no. It's a function. The left hand, see, the right hand side are values. These are fixed values. Oh God, what did I do? Oh God, yes. All right. No, the right hand sides are fixed values. These are functions of x1 and x2. So the moment you fix the values of x1 and x2, automatically they'll be updated. No? So what it did was it searched for the values of x1 and x2, satisfying the constraint that maximize the objective function. Once we reach those values, automatically left hand side and right hand side is less than equal to 42. Yes. All right. So automatically it does that. It's not that it's auto-populated. Because everything is a function of x1 and x2, when you put in the values of x1 and x2, everything automatically gets in terms of yes. Okay. So that's why I made it a function of those two cells. When they found the values of these, automatically everything gets updated. Those are the variables. No, those are input cells. Those are input cells. Yeah. No, those are input, variables. Oh, those are the left-hand side. Left-hand side should be, see, all the variables have to come on the left-hand side. So these were functions of the variables. These should be less than equal to these, the right-hand side. Right-hand sides have to be constant. Okay? Yeah, of course. That's how we do it, naturally. So for example, if the profit of this increases a little, suppose it becomes 15, will that change the solution? We can just solve again. So just go to data, solve again. Will it change the solution? No, nothing has changed. And so on, right? So we can do all that. All that is what we're coming to next, sensitivity analysis. Means? You can put 0 at the end or something. You can put left hand side equals 0 automatically. Oh no. Or put some large value on the left hand side. No, because any number of constraints can happen. No? Is there a fixed number of constraints that happen? No, but once you've understood how to formulate it, it's not difficult after that. You can create this model anytime. No? Okay? Why do you need a template model for it? You don't need a template really. No? And in different contexts, sometimes there will be greater than equal to constraints, sometimes equal to constraints. Putting a template for that isn't really useful. Okay, anyway, no problem. So, all right, so everyone has understood how to use these? Okay, so now, so please try to finish the rest of these. There are a couple of other problems here. Try to go through all of these. They're quite simple actually, not very difficult, very similar to what we've already done. So I'll just save that. And I'll go on to, okay, this was, all right. Okay, let's do one with 4 variables, all right? So here's a product mix problem, all right, with 4 variables here, okay? So what do we have? We have 4 products. I don't know, anyhow, A, B, C, D, let's call them. Otherwise, X, J, 2, 0. Anyway, A, B, C, D, let's call them. So 4 products. And there are 4 departments: wiring, drilling, assembly, inspection. Okay? And these are the unit requirements of each product in each of the departments. So for example, product A requires 0.5 what? hours, 0.5 hours of wiring, 3 hours of drilling, 2 hours of assembly, and 0.5 hours of inspection. The second product requires 1.5 hours of wiring, 1 hour of drilling, 4 hours of assembly, 1 hour of inspection, and so on. These are the capacities of each. Okay, these are the capacities of each, 1,500 to 1,000 hours in each of the departments. These are the minimum production level that we require. So we must produce at least 150 units of the first product, 100 units of the second product, and so on. And these are the profit contributions of each of the products. So first product gives us a profit contribution of 9, second product 12, and so on. Okay? So what are we trying to decide here? Okay, look, don't worry. Are we writing the exam tomorrow? So please, let's not worry about the exam already. Let's first try to learn and then get to the exam, okay? Without learning anything, there's no point writing an exam. Yes or no, Vivek? I really detest people who ask about exams in the first class itself, actually. Right? Please, if you're just coming to write an exam, why do you listen to class anyway? Just write the exam directly. What's the need? All right, so I'm sorry, Vivek, but please don't worry about the exam now. First, let's learn everything, and then we'll see what to do for the exam, okay? The first thing that, so what's coming in the exam? We're small children. People are supposed to be executives as well, no? All right, so what are we trying to decide here? Just as usual, how many products of each type to be produced? So number of units of product of each type, product A, B, C, D, to be produced, given our capacity constraints in each department, and given the minimum product level, and we want to maximize the total profit contribution. Okay, so can I directly solve this in Excel? Would that be okay? That'll be okay? Yes? You can clearly see the formulation from Excel only, right? Yes or no? What about the online people? It's okay if I directly wrote everything in Excel. I'll explain it, don't worry. Okay? So, let's proceed with this. So, what are the different products? Okay, of course, you can't say no, really. All right, so, what are the different products? Product A, B, C, D. Okay, let's call it A, B, C, D. So, A, B, C, and D. Okay, instead of those names, I'm giving them products A, B, C, D. Okay, and just to make it look nice, I'm making them yellow. Just to highlight them, I've made this up. Now, what is the next thing I need to put in? The objective function. No, the objective function first. So, what is the objective function? Total profit contribution. Okay, total profit contribution. And if I'm not wrong, first one is 9, 12, 15, 12, 15, and 11. Yes or no? Yes. Okay. Now, what are the departments? Wiring, drilling, what were they? Wiring, drilling, assembly, inspection, and inspection. Okay, and what we need to do is we need to take the transpose of this. It's done ulta actually. So the product should be in columns and the department should be in rows. So 0.5, 1.5, 1.51 should become the first row. So 0.5, 1.5, 1.5, and 1 should become the first row. Second row is what? 3, 1, 2, 3. 3, 1, 2, and 3. Third row is, oh, what was that? Third row is 2, 4, 1, 2. Oh, God, where did it go? 2, 4, 1, 2. 2, 4, 1, and 2. And last row is 0.5, 1.5, and 0.5. 0.5, 1, 0.5, and 0.5. Okay? Now, one more thing. Minimum of A, B, C, and D, we also have to put. There are 4 more constraints, right? Minimum quantity of A to be produced, minimum quantity of B to be produced, minimum quantity of C to be produced and minimum quantity of D to be produced. And what is it? Basically, see, so these will be 0.5x1 plus 1.5x2 plus 1.5x2 plus 1x4 should be less than or equal to 1500. 3x1 plus x2 plus 2x3 plus 3x2 less than or equal to 2350 and so on. But these minimum production levels means that x1 has to be greater than or equal to 150. x2 has to be greater than or equal to 100. x3 has to be, so each variable has to be greater than or equal to that. So that will look like an identity matrix here. Right? So we're saying that x1 has to be greater than or equal to 150. x2 has to be greater than or equal to, and so on. Okay? And now we can form our constraints, functions. So now, in the other case, what I did was I multiplied each coefficient with each variable. But with 2, that's okay. But if we have many of them, that becomes tedious. So anyone knows a nice way of multiplying 2 rows together? 2 rows. I have 2 rows which I have to multiply together like that. Well, it's called the sum product. Okay? Sum product allows us to take 2 rows and multiply corresponding elements into each other and add them. Okay? So, sum product does this in a very efficient way. Oh, sorry. Very efficient way of doing this. Okay? So, oh my God, what is that? Okay, so sum product, and I'm going to copy this all the way down. Now, the first few constraints are less than or equal to the capacity, and these constraints are greater than or equal to the requirement. Okay, these requirements were 150, 100, 300, 400, right? 100, 300, and 400. And what was the capacity? 1,500, 1,000, oh God, 1,500, 2,300, was it? 2,350. Funny thing was that. 2,600, sure. And the last one is 1,200. Okay? And now we can solve this. Where is it? Sorry. Okay, so everyone is ready? Oh God. Okay, solver. So, this was my objective, to maximize total profit. These are the variables A, B, C, D. Now, the first 4 constraints are less than or equal to type. Left-hand side, less than or equal to right-hand side. Okay. Next 4 are greater than or equal to. So, next 4 are greater than or equal to these 4 right-hand sides here. Very simple, no? And of course, simplex. Okay. We'll look at sensitivity. So, our final solution is produce 150 units of first product, 100 units of the second product, 300 units of the third product, 400 units of the fourth product. Well, of course, this is exactly the required levels, huh? Exactly the required levels. So, we're not doing anything in excess. This is exactly the minimum required levels. So, in other words, oh, I see. Interesting. Huh? Why do we put for, oh, okay, yes. See, basically, what is that constraint? So, the constraint here was minimum production level. So, minimum production level of the first product is 150. So, how would we express that as a constraint? X1 is greater than or equal to 150, right? So, when you put that as a coefficient, what is the coefficient? Coefficient of x1 is 1. So, 1 into x1 is greater than or equal to 150. That's what we're saying there, okay? Right? All we're writing down, see, that's the nice thing. All we need to do is write down the coefficients and then multiply by the corresponding variable. But this is peculiar, no? Very interesting. You get exactly only the minimum required, right? Am I sure I did this? Yeah, maximize. Right? So then we're not going beyond any of the minimum requirements. Strange. Okay? And no, maximize. We're maximizing total profit here, right? We didn't minimize here. Okay, I checked that as well. See, I've gone to solver and we're maximizing. If we minimize, I think we'll get the same solution, of course. Yeah, we'll get the same solution, but actually what is exact here? Exact means? Exact because, see, now why I'm saying exact is, see, our minimum requirements were exactly these, right? 150 for A, 100 for B, 300 and 400. And we're producing exactly that much. So that is why it's peculiar. Because minimum requirement is minimum requirement. If something is more profitable than that, then we may want to produce more of that. But we're producing just the minimum requirements. That's what is peculiar. That's what doesn't seem to be correct. But anyhow, there's nothing wrong with it. So, okay. So always you have to get, well, it depends, right? It depends on the context of the problem. Here, when we have profit contributions, we're maximizing. Right? So that's the thing. All right. So shall we try another one? Okay. Oh, they've formulated it. Yes. Okay. Same thing. Okay. All right. Here's a diet problem. Same type of thing. This is interesting. Okay. So let's try a labor scheduling problem. Okay. Labor scheduling problem. Okay. So what is the minimum? Minimum is full time. Okay. All right. Okay. So here's a nice type of thing. So we have a bank. Okay. In a bank, there are a certain number of tellers that are required. So depending on rush hour and things, we may need more tellers in some periods than others. So suppose, for example, in period 9 to 10, we require 10 tellers. In period 10 to 11, we require 12 tellers. 11 to noon, 14. Noon to 1, 16, and so on. All right? So all this is the requirement of tellers. Now the thing is, we may decide that, okay, we don't want full-time people only. So we can have a certain number of full-time people and a certain number of part-time people. Okay? Now, full-time people will work for, I think, 8 hours, will work all day, right? Whereas part-time people will work only for 4 hours, and either they can start at 9 o'clock and work for 4 hours, leave at 1 o'clock, or they can start at 10 o'clock, work until 2 o'clock, or start at 11 o'clock, leave at 3 o'clock, start at noon and leave at 4, or start at 1 o'clock and leave at 5. So these are the options available. How many full-time workers and how many part-time workers starting at different points of time should we hire so as to reach or have the minimum requirement of tellers in each of the time periods. Okay? And it's very simple. So the full-time tellers will be there all the time. Of course, we want to minimize the total cost. The costs are given in the next slide. What are the costs? The costs are $70 for full-time employees and $24 for part-time employees. Okay? Okay, whatever. Anyhow, that's given to us. We can change that. So the total cost is 75 into F plus 24 into P1 plus P2 plus P3 plus P4 plus P5, depending on how many we actually hire in different time periods. Right? The same problem can be solved by minimization. Yes, I know. That's why Rajesha was saying in the previous problem, minimizing and maximizing give the same solution by chance. Okay. So that's the by chance in the previous problem. Anyway, here we're definitely trying to minimize. Okay, we're minimizing the total cost of keeping these number of tellers available at the time. Okay. Now, how do we put in the constraints? Well, it's something like this. Okay. Oh, sorry. Okay. See, we need 10 people, 10 tellers at 9 to 10. So the full-timers will be there. So F full-timers will be there. Now, how many part-timers will be there? Those who have joined at 9 o'clock. So the tellers available at 9 o'clock are F plus P1. So F plus P1 should be greater than or equal to 10. Right? Everyone can understand this, huh? Very, very simple idea. The full-timers are there whole day, so F will be there. And part P1 are part-timers who have joined at 9 o'clock, so they will also be there for that shift. So in the first shift, F plus P1 should be greater than or equal to 10. Now, what about second shift? Second time period. Again, the full-timers are there. The part-timers who joined in the previous period are also there. So F plus P1 is there, plus P2 people have also joined. So in the second time period, F plus P1 plus P2 should be greater than or equal to 12. In the third period, F plus P1 plus P2 plus P3 should be greater than or equal to 14. In the fourth time period, F plus P1 plus P2 plus P3 plus P4 should be greater than or equal to 60. In the next time period, what happens? The P1 people drop out. So F plus P2 plus P3 plus P4 is greater than or equal to 18. Then the P2 people drop out. F plus P3 plus P4 should be greater than or equal to 17. Then the P3 people drop out, and so on. Okay? So, oh no, some people are, so there's P5 also, sorry. Plus P1 has dropped out, P2 plus P3 plus P4 plus P5 should be greater than or equal to 18. Then P3 plus P4 plus F plus P3 plus P4 plus P5 should be greater than or equal to 17. Then F plus P4 plus P5 should be greater than or equal to 15. And then F plus P5 should be greater than or equal to 10. That was a bit of a tongue twister actually, but okay, so this is how it's shown. Oh, half F. Huh? Why half F? Oh, I see. Lunch break. Okay. So this is something that we should have to read from the question. I didn't read the question. So, all right. So 9 to 10, F plus P1 should be greater than or equal to 10. 10 to 11, F plus P1 plus P2 should be greater than or equal to 12. Then half the people go on lunch break from 11 to 12. That should have been 12 actually, 11 to noon. And half the people go from noon to 1. So that's why half F here, half F here, P1 plus P2 plus P3 here, plus 1 plus P2 plus P3 plus P4 there. And then slowly, one by one, they start going home. So P2 goes away, then P3 goes away, P4 goes away. And at the end, we should have at most 12 full-time people. Okay, some extra constraints may be imposed by management. And, the number of part-time hours should be less than or equal to this. Total number of, this is the total. Okay. 4 times this, okay. Okay, only half of this should be, maximum half of this should be done by part-time people. Okay, that's what the last constraint is. Okay, so last constraint is that. Shall we solve this quickly? Okay, why not? All right, so, okay, this is an interesting problem. All right, so let's go here. So S, P1, P2, P3, P4, P5. So I think it just copies, yes. All right, these are our variables. Okay, these are the variables. And we're trying to minimize the total cost, right? Total cost, which is, I think, 75 for this and 24 for each of these. So let's copy this 24 across. Then period 1 to period. How many periods are there? 1, 2, 3, 4, 5, 6, 7, 8. 8 periods. I'm sorry? Okay, sure. Okay, yeah. 8 periods we need here. Okay, 8 periods. All right. Now, full-time workers are there for these 2 periods, and then next 2 periods, 0.5, and then rest is 1. Okay? And now, basically, these are there for these 4 periods. These are there for these 4 periods. These are there for these 4 periods, and so on, right? Very simple. Okay? Okay? Very, very simple structure, right? When a part-timer joins, they work for 4 hours and leave. Right? Very simple. And now we take sum product. So sum product of these coefficients with these variables and dollar signs here. Okay? And we'll copy this on the left-hand side here. Oh, that's not all the constraints. Then I think maximum full time is how much? Less than equal to 12 also, right? So this is less than equal to 12. And then there was one constraint about maximum part-time work, right? So maximum part-time work, PT hours, was how much? So 4 into this is less than equal to that. So, okay, maybe shall I divide by 4 on both sides? Shall I divide by 4 on both sides? So I'll take 0.5 into 112 divided by 4. So 112 divided by 4 is how much? Okay, 112 divided by 2 is 56. 56 divided by 4 is 14. Okay, so maximum part-time hours is 14. So we'll put 1, 1, 1, 1, 1, 1. Oh, not here. Is less than or equal to 14. Okay, so maximum is less than or equal to 14 here. And these are all greater than or equal to constraints, right? Greater than or equal to how much? The manpower requirement in each period. So manpower requirement here is 10, 12, 14. 10, 12, 14. Then comes 10, 12, 14. 16, 18, 17, 15. 16, 18, 17, 14, and I think 10 at the end, right? Let's remove 10. Okay. All right. So we're ready. Oh, there's some query. 28. 28. 15. 28. 15. Which one? Left hand side here. So this is 0.5 into 112. That is 56, right? 56 divided by 4 is 14, no? No, not 14. Not 56. No. After 17, no? Oh, that. Sorry. Okay. This one, I see. Okay, thank you. All right? Yeah. Okay, so now let's do it. Let's solve it. Okay? So here is our, just one last step. Let's make this. Okay, so we'll go to solver. We're this time trying to minimize the total cost. Be careful. Where are the variables? These are the variables and constraints. Okay, first of these constraints, all of these constraints are greater than or equal to these values. And the last two constraints are less than or equal to. Okay. And here we are. Okay, so 10 full-timers, 7 part-timers starting at 10 o'clock, 2 part-timers starting at 11 o'clock, and 5 part-timers starting at noon. That's the minimum required number of. Okay, so very simple. So you can actually go further. Different types of specialists that you can optimize what is the optimal mix of faculty or employees that to achieve certain objectives. Okay, very, very nice actually. Right? Right? So why last two are less than equal to? Okay, yes. And that I think came from the problem. It wasn't actually mentioned in the, so unfortunately we don't have to see the problem itself, but the problem, it should have mentioned what is the maximum number of full-timers and what is the maximum allowable time given for part-time. I think that's what these two are. So that's why it's a less than equal to. Okay, so this is our solution. Huh? First solution, oh, I see. There are two alternate solutions. Oh, multiple optimal solutions. I think we got this one, 7. No, I see we got an even another one, huh? Yeah, we got 3, in fact, huh? That's interesting. Both will cost 1086. Okay, anyway, so before we get carried away, we have to do something else. Okay, so go through the rest of these things. We will be talking about sensitive numbness in our next class. We won't have time to do all that now. So let us do one more thing, which is, what is that one more thing? Oh, 2 and 3 is done, is it? Did I do? No, I've done this. Yes, I finished this. Where is 4? Anyone can see 4 somewhere? Okay. It's more or less the same actually. It's not any different. Same only. All right, no problem. So this is done. 5. Where is 5? Yes. Okay. So now, what happened? Okay. So. Okay. All right. So now we're going to look at something called the simplex method. Okay. So we just have about half an hour of that. Not even half an hour. Okay. So we'll see how to do the simplex method. All right. So this is a method that allows us. Why isn't this allowing us to go full screen? What is happening? Okay. What is happening? Okay, fine. Okay, so now the next thing is a method called the simplex method. Okay, so we'll talk about a method called the simplex method. Now the simplex method is an algorithm for solving linear programming problems. We'll see. If you're not comfortable with it, then we'll find a way of avoiding it. It's a bit of a sort of, well, basically, see, we've learned how to solve graphical problems, that is, 2-variable problems. Now, when it comes to many variables, of course, we cannot apply graphical methods. For example, if we have 4 variables, we can't even draw a graph for it, right? Of course, we've seen how to use these solvers to do this, but sometimes we need to go a little in depth to understand where the solution came from. So in that context, I want to sort of explain a little about the simplex method that is used by all these solvers to solve the LPP. Okay, so we'll be solving some simple problems using simplex method. Okay, now of course we've already discussed the graphical method. Very colorful type of presentation this is, but anyhow, so let's forget about all these things. Anyway, you can go through this. This explains it in a lot of detail, actually, how to draw graphs and which side, this side, that type of thing. Okay, so, all right, so please go through this later if you have, well, of course, you'll have time, so make sure you go through this later. So, okay, so here I'm looking at a okay, so, all right, so this is the problem. So let's start with this problem and see how to understand it. Okay, so Ace Novelty wishes to produce two types of souvenirs. Type A will result in a profit of $1. Type B will result in a profit of $1.20. Okay. Okay. To manufacture type A souvenir requires 2 minutes on machine 1, 1 minute on machine 2. Type B souvenir requires 1 minute on machine 1, 3 minutes on machine 2. 3 hours are available on machine 1, 5 hours are available on machine 2. So, how many souvenirs of each type should Ace make in order to maximize its profit? So, this is just like all the other problems we've solved, so no problem at all to formulate this. So, we're trying to find how many souvenirs of each type to produce with the given machine times available so as to maximize our total profit. So, we're maximizing x1 plus 1.2 x2 subject to 2x1 plus x2 less than or equal to 3 hours. 3 hours is how many? 180. And x1 plus 3x2 less than or equal to 300. Okay, that's what we have. X1, x2 non-negative. Okay, so this is the thing again. So maximize x1 plus 1.2 x2 subject to 2x1 plus x2 less than or equal to 180, x1 plus 3x2 less than or equal to 300. Okay, so okay, so our total. So we've seen this so many times we don't even need to go through this here. Okay, so now we're going to solve this using what is called the simplex method. Okay, they'll solve it graphically. We won't worry that much, and this is we'll come back to this. Okay, so this is the graphical solution of that same problem. Okay, so all right, all in. All right, so same problem solved graphically. This, then the overlap, then the feasible points, and this is our optimal solution. Oh, I see. Okay, I've done something else there. Okay, so the optimal solution is 48, 84. So 48 souvenirs of type 1, 84 souvenirs of type 2 will maximize our profit, and the profit is 148.8. Okay. Okay, now let us see how to solve this using the simplex method. Okay, so now the simplex method is a procedure. Well, it's really a matrix method for solving this. So what we're doing is we're doing something called pivoting. Okay, we're doing something called pivoting, and the idea is okay. All right. Right. How many of you remember a little of matrix theory? Matrices? No, not much. Okay, all right. Well, anyway, when we do it, then I'll explain how it links with the usual matrices. Okay, so first of all, we need to produce we need to write this in what is called standard form. Okay, so we take our problem and we express it in standard form. Now, to be in standard form, first of all, the objective function has to be a maximization problem. All the variables must be non-negative, that's anyway there. The linear constraints must be, all other linear constraints must be written so as they're less than or equal to a non-negative constant. Anyway, that was already there, right? Okay. Now, what we do now is, for these, for the things, for each of the constraints, we introduce what are called slack variables. All right, so what did we do? So, okay. Oh, this is rewriting the objective function. Actually, we don't need this, so don't follow this. I don't like this approach. Okay, so what we have is, our objective function is x plus 1.2y. Let's not follow that minus convention. Here what we're going to do is, for the constraints, we're going to add a slack variable to each constraint to make it equality constraints. So, all right, so what we do here is, okay, so for the first constraint, 2x1 plus 2x plus y less than or equal to 180, I add a slack variable to make it equal to 180. For the second constraint, x plus 3y less than or equal to 300, I add a slack variable v to make it equal to 300. Now, what are these things? Basically, the slack variables are the quantity of resource left over. So, if I'm using up all the resources, the slack variable will be 0. If I'm not, that is left over. So, I'm using this much. Whatever is left over, total has to be 180. Okay? So, that slack variable measures how much of the resource is left over. Okay, now, they rewrote the objective function, but we'll use a different method, so we'll see. Okay, so now we're rewriting the constraints as follows, and we get the initial tableau as follows. Okay, now the initial tableau works like this. Okay. Now, my initial tableau works like this. So, we take the constraints and write them in structural form. So, the variables, each variable, I'm giving a separate column. So, x, y, u, v, and on this side, constant. X, y, u, v, and constant. Ignore this p. Anyway, we're not going to use it. Actually, we don't need it. Okay? So, now, write down the coefficients. 2, 1, 1, 0, 180. 2, 1, 1, 0, 180. Ignore this P column. 2, 1, 1, 0, 180. And the other one, 1, 3, 0, 1, 300. 1, 3, 0, 1, 300. Now, the delta J column. Okay, so, now, basically, how this simplex method is going to work is we're going to use this identity matrix. Okay, so everyone can see the identity matrix here? Anyone can see an identity matrix here? Okay, this is the identity matrix, correct? Now, we're going to use this identity matrix in a nice way, okay? Now, what we're going to do is we're going to define what is called a basic feasible solution. Let me change the color of this. Okay, so I'm going to define something called a basic feasible solution. Okay? Now, basically, see, where my identity matrix is, I'm going to define as the basic variables. So, u and v are the basic variables here. And basically, this is a simple way of solving. See, we have a system of linear equations here. 2x plus y plus u equals 180, and x plus 3y plus v equals 300. Can anyone think of a very simple way of solving this system? Well, one simple way is, see, I have u equals and v equals here. If I put x and y equal to 0, I can just read off u equals 180, v equals 300. Yeah, isn't that a nice thing? Okay, so basically, that's what I'm defining as basic variables. Non-basic variables are variables that I'm setting equal to 0. And the basic variables, I'm setting equal to the values on the right-hand side. So, in this, so there are 4 variables, x, y, u, and v. The non-basic variables, x and y, are set equal to 0. And because of the nature of this identity matrix, I can read off u equals 180, v equals 300. In other words, what I'm doing is, because of this nice identity matrix here, I'm reading off u equals 180, v equals 300, and I'm ignoring all the other variables. All the other variables are equal to 0. Okay? Now, P, as I'm saying, just ignore this column. That actually is not at all useful. we don't need this column at all actually. You'll see why. Okay. Now, the thing is as follows. What we'll do is, okay, to start with, okay, to get, see, now in the current solution, the current values here, all right, the current variables are u and v. U equals 180, v equals 300. So which point are we at? Well, in the graph, we're at the origin because x and y are both equal to 0. And that's why z is also equal to 0 here. Okay, we're at the origin. So actually x and y are both equal to 0, and so z is equal to 0. Now, to see whether we're optimal or how we can improve this, we're going to calculate these delta j's. And we do that by first looking at the objective function coefficients. What are the objective function coefficients? They are 1 and 1.2. There it is, right? Objective function coefficients are 1 into x and 1.2 into y, right? So I'll write them here as 1 and 1.2. Yes? 1 and 1.2. And what are the basic coefficients? What are the basic coefficients? That is, the basic variables are u and v. What are their coefficients? Actually, they're 0, right? The basic variables u and v do not enter into the objective function. So, basic coefficients in this case are both 0. And now I'll calculate something called my net evaluation as follows. I'll multiply these into these, so 0 into 2 plus 0 into 1, and subtract Cj. So Cb into each column, so 0 into 2, 0 into 1, minus Cj will give me this row here. 0 plus 0 minus 1 is minus 1. 0 plus 0 minus 1.2 is minus 1. 6 by 5 is 1.2. This is 0 plus 0 minus 0 is 0. 0 plus 0 minus 0 is 0. And the whole idea is, when this delta j column becomes non-negative, I've reached my optimal solution. When I reach a point when delta j's are all non-negative, that's the optimal solution. Okay? So currently, because some of the delta j's are negative, this is not optimal. Now, what I need to do therefore is I need to move from this point to the next point. Now, how I do that is as follows. I choose the most negative delta j here as my entering variable. In other words, see, currently y is equal to 0. Now I'm going to make y positive. So I'm going to make its value positive so that now it will contribute to the objective function. But here, since y was a non-basic variable, and since there are only two basic variables allowed, one of the basic variables has to be transformed into non-basic. To decide which one of those to take, I'll calculate theta as follows. All right? So in this pivot column, this is called the pivot column, I'll take the b value divided by the corresponding coefficient here. So 180 divided by the coefficient here, 180 divided by 1, and here 300 divided by 3. And I select whichever is least. So which one is less, 180 by 1 or 300 divided by 3? Which one is least? 300 divided by 3. And so this becomes our pivot. This is called the pivot entry. And now my identity matrix will come here. U and Y. U and Y will now be the identity matrix in the next step. Okay, so what we say is this basic variable exits the basis and is replaced by Y. So in the new table, U and Y will be the basic variables. Okay, so let's see what's happening. I'll set up the initial tableau and so on. Okay, so same thing has been done here. Basic variables, and this is our pivot, and this is the exiting variable. Same thing done in this step here. Okay, I did it one step before this time. Right? Did everyone follow, or should I do it again? Okay, so let me do it again, no problem. Or maybe, anyway, we'll see whether we can finish it now or we can do it next time. It's no problem. Oh, hey, it's not rubbing. I can rub out previous things? Huh? So I can't rub it out now, is it? Oh, God. Okay, so then we've only got around 5 minutes left. Should we do this next time? All right, I think that's a better idea then. Okay, so we'll do this method next time. Okay, so let's just do some more. Okay, since we have 5 minutes to kill, we'll solve one more problem. Okay, so we'll just solve one more problem. And okay, so which other problem was left? I think, okay, we can, you want to break, huh? Okay, otherwise, shall we carry on from here next time? So we'll start with the simplex method from here next. All right, so any doubts or anything anyone wants to discuss before? All right, yeah, please, of course, go through it. Try solving, practice using Excel, that's also very important. Practice using Excel, practice formulating, and even the textbook. Try to solve as many problems in that as possible. By the way, since I gave you this textbook yesterday, there are around 60 to 80 problems in this also. So you can try these. They're very interesting because they give a range of different applications. Here they became very repetitive. Product, this and so on. Here you have lots of problems on investments, on other things as well. So try this chapter, chapter 2. We're basically on chapter 2. So to try the chapter 2 problems and, all right, so chapter 2 is the graphical method and all these very interesting types of problems you have here, right? So around 50 problems if you can all try. And solving, you can solve in whatever, Excel or whatever, but at least try to formulate them. Very, very interesting, some of them. Okay, so there are some doubts here also. We need to revise simplex. No, we haven't done it, sorry. No, Rajesh, we haven't, we did one step and that too not very completely. So we'll start the simplex method next time, okay? All right, so don't worry. And any other doubts? Any of you online? No? All right. So we'll meet again. I think not next week, but week after that. Okay. So, all right. So let's.